All right, so for our last talk, we're happy to have Renzi from University of Zurich, talking about quantum and homological representations of mapping class groups of surfaces.
Okay, thank you very much. And since I'm the very last speaker at this conference, I propose we all thank the organizers for organizing such a very nice conference. So thank you very much. I maybe clap. Okay, and thank you very much for the invitation. I'm sad I couldn't be there in person. I would have really loved to be there. I'm happy anyway I had the chance to attend virtually, so thank you very much again. And today I will present a work in progress, which is a joint work with Jules Martel. And the goal of this project is to relate two different constructions of the same family of representations of mapping class groups of surfaces. And the main message of my talk will be that these two approaches, they describe the same representations, but they each have their own advantages and they can inform each other and hopefully further our understanding of the properties of these representations. Right, so on one hand, we have the quantum approach to topology, so the approach of quantum topology that was greatly developed by several people. I should at least mention Turayev, who formalized in great generality the so-called original semi-simple approach to the theory. I should also mention Lyubashenko, who generalized deeply Turayev's approach to a non-semi-simple setting that will be the most relevant setting for everything I'm going to say today. And in quantum topology, we typically have a wealth of constructions, so a lot of invariants. We typically are able to construct link and three-manifold invariants, but also representations of mapping class groups of surfaces, and even more general representations of cobordism categories, which are called TQFTs. So this is short for topological quantum field theories. They popped up many times during this conference. And the methods used by quantum topology are rather algebraic. And the advantage of this approach is that it provides highly organized invariants, as it is witnessed by the several layers of constructions we have here that are all coherently organized by this refined notion of TQFT. But these constructions are also very general and flexible, right? So indeed, so in quantum topology are typically based on certain algebraic ingredients, such as quantum groups, or maybe more general Hopf algebras, or even more abstract ribbon categories. And for these algebraic structures, we have a fully developed theory of their own, and in particular, a lot of examples, of concrete examples. And for each concrete example, we have the associated three-manifold invariant and mapping class group representations, and even TQFTs. So this is all very general and flexible. This is very nice, but on the other hand, this approach has these constructions have a very abstract flavor. And while performing these constructions, we quickly lose sight of what kind of topological properties are measured by the invariants we are constructing, right? To the point where the topological content of quantum invariance is typically the subject of all the deepest and all the hardest conjecture in the domain, right? So on the other hand, so on the other side of the slide, there is the so-called, well, at least I'm calling this the classical approach. So classical is a very broad and generic term, and one might object to the terminology here. I'm using classical in contrast with the quantum term on the other side of the slide, but I will mainly refer to a very specific class of constructions, which is originally due to Ruth Lawrence, who constructed in the 90s representations of braid groups using homological methods. So in particular, her representations are built using twisted homology of configuration spaces of punctured disks. And you should think that braid groups, as it was mentioned in the previous talk, they can be understood as mapping class groups of punctured disks. So they kind of fit as a subset of this middle construction on the left side. And the advantage of the approach of Lawrence is that it allows us to retain control over the topological content of the invariants we obtain. This makes room for, this allows for spectacular results, like for instance, the proof by Bigelow that braid groups are linear, right? So it turns out that these representation defined by Lawrence, they are equivalent, they are isomorphic to certain representations that arise on the quantum side. This was proved by work of Jackson, Curler, and Kono, and this was recently deeply generalized by my co-author, by Jules Martel. But it's important to notice that, like, Bigelow's proof of faithfulness of Lorentz representations really uses the homological construction of Lorentz. So this is a very powerful tool. On the other hand, from this side of the story, it's less clear how to generalize this construction in order to obtain all the different kinds of structures we have here on the left, right? So the goal I will discuss today is to generalize this classical construction, class groups of arbitrary surfaces, or at least to connected surfaces of arbitrary genus, to relate this construction to the quantum one we have here on the left. And the motivating question behind this project is whether mapping class groups are also linear. This is an open conjecture, and this is a very hard question. And we could think about this project as aiming at developing the tools that, or at least the analogs of those tools that were used successfully by Bigelow in order to prove linearity of braid groups. So I've seen a warning that my connection is unstable. I'm sorry, I'm having small connection troubles. Please interrupt me if things go badly, but I hope it will be as stable as possible. Anyway, I will now maybe move on to giving an overview of the main result I will present today. And I will start from the quantum side of the construction. And to do this, I will need to fix some notation. So I will denote with sigma G1 genus G surface with one boundary component, right? As represented in this picture. So for some reason we like square boundaries. There's, I mean, maybe I will provide some comments later on, but anyway, here you should think that the boundary of this square is the one component boundary of the surface, and then the surface is obtained from the square by attaching G copies of a one handle. And I will never write this down explicitly, but all surfaces and manifolds I will consider today will be oriented and connected. So this is the case here. Then I will denote by mod sigma G1 the mapping class group of this surface. this is by definition the group of positive diffeomorphisms of the surface sigma G1. By positive, I mean that they should preserve the orientation. They should also fix the boundary point-wise. I am modeling out this group by the normal subgroup of those diffeomorphisms that are isotopic to the identity. So essentially, we are considering diffeomorphisms up to isotopy. And then the main algebraic ingredient I will use for quantum constructions will be denoted this lowercase u. This is short for SL2. And this is the small quantum group of SL2 at a root of unity q, which we set equal to e to the 2 pi I over r. And r here is an odd integer greater than 3, or at least 3. I will provide a precise definition for this quantum group. For the moment, I'm just telling you that this is a rich algebraic structure. This is a finite dimensional algebra, and we can use it to do all the constructions we like in quantum topology. And I also fix a notation, rather self-evident notation for the adjoint representation of the small quantum group. I will denote this ad. And this is a left U module structure on the quantum group itself, given by the adjoint action. I will also give a precise definition later on. But for the moment, this notation allows me to state the main result on the quantum side, which is that, first of all, U induces a TQFT. I haven't defined what a TQFT is. I guess most of you know, and it appeared also in previous talks. It won't be really necessary to know the details of the definition for this talk, but it's just to tell you that with this example of algebraic ingredient, we can perform all the constructions we liked on the previous page, on the left side of the previous page. Right, and since U induces a TQFT, in particular, it also induces a projective representation for the mapping class group of sigma G1 in the projective linear group of the Gth tensor power of the adjoint representation. And maybe a quick comment here on this notation. This is a compact notation for, in order to denote the group of invertible U-module endomorphisms of this U-module up to multiplication by non-zero scalars. So what I'm saying here is that not only the mapping class group acts by linear endomorphisms, it also acts by really U-module morphisms. So in other words, the projective action of the mapping class group commutes with the action of the small quantum group U on this vector space. And this property of having commuting actions is very useful in order to prove the main result I will state in a moment, right? And this statement here kind of collects together, gathers contributions of several works. These representations were first defined by Lyubashenko back in the 90s, and they were later obtained as the quantum representations induced by TQFT obtained through the universal construction in a joint work with Azat Gainutdinov, Nathan Gear, Bertrand Patureau, and Ingo Runkel. And well, I'm stating explicitly here again what is kind of the motivation question behind for considering these representations. We kind of would like to understand what is the topological content of these representations. What do they measure? Right. And now for the main result, I will unfortunately need some more notation. So I use curly h sub g in order to denote this this big vector space, or at least yes, this is a direct sum of certain homology spaces indexed by an integer n between 0 and r minus 1. So let me try to unpack a little bit this heavy notation here. So these are relative homology spaces, meaning that they are homology spaces of pairs. The first term in this pair is the nth unordered configuration space of the surface sigma g1, which means just unordered n tuples of these distinct points inside sigma g1. I will write down a precise definition also later. Then the second term in this pair, some subset of the boundary of this space here, of this manifold. And I will give a precise definition again later. I'm postponing many things, but for the moment, you should just think that this is some part of the boundary of this configuration space. And then we are considering twisted coefficients. So coefficients are in this left z pi module, where this pi and g is the fundamental group of this configuration space. So this is typically called the surface braid group for the surface sigma g1. And this coefficient space v and g is just the vector space c to the power r power g, but it comes equipped with an important action of the fundamental group of this configuration space. So we consider twisted homology, and there are other subtleties. For instance, this BM notation. I will mention later what we mean by this. But anyway, now I can maybe state the main theorem I will discuss today, which is the following. So curly HG admits a U-module structure, first of all, and also a projective representation of the mapping class group of sigma G1. So this will again be with values in PGL U of curly H sub G. And furthermore, these two algebraic structures, they agree with the quantum ones in the sense that curly HG is isomorphic as a U-module to the G-tensor joint representation, and these two mapping class groups are perfect too. And maybe a quick comment on this statement too is that, well, of course, every time you have a vector space of the same dimension as this one, you can kind of use a linear endomorphism between these two spaces to push forward all the nice algebraic structures we have on the G-tensor power of the joint representation. This is very artificial and not interesting and not deep. So what I claim is interesting about this statement is that the U-module structure and the projective representation on the homological side, they are defined in purely homological terms. So they are inherently defined on the homological side, and then we can check that they agree that there exists a linear isomorphism between these two spaces that preserves all these structures. Right. So the goal for the rest of the talk will be now for me to just fill in the gaps I left in this discussion and to give you some definitions that I promised, and to try to explain as much as I can this construction. Right. And I encourage you to stop me anytime if you have questions. Right.
Just a quick, maybe I just missed it. What is R, or R is just parameter you choose?
Sorry, yes. R is the order of the root of unity. It was on the previous slide.
Thank you.
And yes, thank you for this question. This is important. Right. Here we are taking a direct sum that stops at R minus 1. Well, precisely because we are exactly looking at the homological construction that would match exactly the the quantum construction. It's important probably to say that the quantum construction can be, of course, generalized in several ways. We can use several different algebraic ingredients to do this construction. And also the homological construction can be generalized in various directions. And this is some kind of intersection point between the two worlds. Right.
I have another question. So does projective general linear count as linear? Does it answer the original question positively?
I'm sorry, I didn't understand. I heard that you asked something about projective, maybe it's the projective linear group?
Oh, yeah. Sorry. Hi, so does PGL count as linear?
Right, so it doesn't count precisely as linear. So thank you for this question. It doesn't count precisely as linear. We can improve all these representations to linear ones, but of a central extension of the mapping class group. This is something customary in all these quantum constructions that have this kind of framing anomaly that forces us to discuss the honest mapping class group, just in the case of projective representations. But sometimes these can be improved. So the framing anomaly can be fixed for certain surfaces, for simple ones. Two other things I should mention on this point is, well, first of all, that already proving that we have faithful representations of which are projective, or maybe faithful representations of a central extension by Z would be already interesting. And also on the homological side, there is probably hope to have interesting linear, honest representations for a mapping class group. This would be the result of a construction I won't go into explaining for today. But yeah, so I mean, something can be said also in the truly linear sense, but these are really projective ones in general. Right, so thank you for this question. And okay, I will start by giving some details and some definitions on the quantum side. And I will recall just that Q is a root of unity of order R. So it's in particular e to the 2 pi I over R. And again, R here is an odd integer, at least 3. And then small u is, so the small quantum group of SL2 can be defined as an algebra over the complex numbers by specifying generators. So we have just 3 generators, E, F, and K, and just 6 relations, which are quite well known. So E and F are nilpotent generators, so E to the R equals F to the R equals 0. Then K is invertible of order R. And this, this together with the other relations will force the quantum group to be finite dimensional. Then conjugating E by K gives Q to the power 2 times E. Conjugating F by K gives Q to the power minus 2 times F. And the commutators between E and F are given by K minus K inverse over Q minus Q inverse. Right. So this is an algebra, a finite dimensional one, as I said, and it can be turned into a Hopf algebra by defining a coproduct delta, a co-unit epsilon, and an antipode. So these are linear maps. So this one goes from U to U tensor U. This one goes from U to the base field, and this is an endomorphism, a linear endomorphism of U. And using this Hopf algebra structure, we can define the structure of a U representation on U, which is the adjoint representation in the Hopf sense. So by definition, this is just the vector space U equipped with the following action. So an element X acting on an element Y is obtained by taking the coproduct of X, then multiplying Y from the left with using the left component of the coproduct, and from the right using the antipode of the right component. And here x1, x2 is an abuser notation for the coproduct. This is very common. This is Sweetler's notation. In general, general coproducts are linear combinations of pure tensors. They're not always pure tensors, but this should be understood as a linear combination of terms of this form. Okay, so this is the adjoint representation. And now I will give you formulas for the action of the mapping class group, so the projective action of the mapping class group on the Gth tensor power of the adjoint representation. I will give formulas just for generators of the mapping class group, and the generators I will use are, well, licorice ones. So it's a famous theorem of Dan and Licorice that tells you that the mapping class group of sigma G1 is generated by a finite set of Dan twists. It's sufficient to consider these curves, and in fact this system is redundant, but it's not a problem. So the curves alpha j are kind of meridians for these one handles. Then you have longitude curves, these beta j curves, and then we have gamma k's that are curves that encircle two different one handles. And so we have G many of alpha and betas and G minus one many of gammas. And right, so I will give you some formulas. Formulas on their own are not very enlightening. So I would like to give you explicit formulas in order to show you that everything is very explicit, can be explicitly computed. But before giving you the formulas, maybe I should tell you a little bit what's the idea behind these formulas, how they are obtained. And if you believe that a picture is worth 1,000 words, I will show you some pictures and try to tell you how these how from these you can derive the formulas that I will show you in a moment. Right. So the idea is essentially that the action of generators of the mapping class group can be computed through a certain diagrammatic calculus, as it always happens in quantum topology. And the definition of the quantum representation uses really the TQFT, so it uses cobordisms, and in particular the fact that every element of the mapping class group can be essentially identified with a cobordism, which is called its mapping cylinder. And so this action is defined using mapping cylinders, and I will tell you how to represent diagrammatically mapping cylinders for these Dan twists. I will use Habiro's notation for bottom tangles in handle bodies. So in this picture right here, you should see for the moment just a genus 2 handle body of dimension 3. So this is just a three-dimensional cube with a pair of one handles attached to the top base. And you can already understand this as a relative three-dimensional cobordism between a genus 2 surface on the top with one boundary component and the genus 0 surface on the bottom, so a disk, again with one boundary component, and the two boundaries are glued together. And now, if we want to represent more general cobordisms, I claim that a picture like this would, for instance, represent a cobordism between a genus 2 surface again, but this time on the bottom, I claim we should see a genus 3 surface. And the way to see this is you should look at these tangle components, these R components that are in a bottom tangle configuration, which means that if you start from boundary point on the bottom and you go through the strand, you should end up next to where you started. And now if you remove a tubular neighborhood of these, if you carve out from your handle body a tubular neighborhood of these curves, you should see appear on the bottom a genus 3 surface. And in this case, we also have a small closed component. And when you see a closed component, you should not simply remove it. You should also glue it back by performing surgery as prescribed by the framing. So all these pictures are framed, right? Okay, so in particular, this is a way of representing an example of cobordism between a genus 2 and a genus 3 surface. And to simplify the notation, I will represent cobordisms by a projection against a vertical plane like this. So this is the same picture I had before, just projected. And using this graphical notation that again is due to Habiro, this is how the identity cobordism would look like. I claim that if you remove a tubular neighborhood of these blue curves, you should see a product structure on the cobordism you have left. And now the other claim is that, well, these specific pictures, they represent mapping cylinders for the generators of the mapping class group, right? So this is a twist against along a meridian here. And these dots denote that everywhere else I have identity pieces of the cobordism. But on the jth piece, here I have a twist. Then this is a twist along the, and this is a twist that mixes to one handles together. Right, okay, so this is not meant well, very detailed. It's just to tell you where the formulas I'm showing you right now, where do they come from? They come from a diagrammatic calculus that uses those pictures, insert elements of the mapping class group at crossings and gathers them together according to some algorithm and produces these formulas. Very good. These formulas, it's not really important maybe to absorb all the details of these formulas. What's important is that, okay, these formulas, they're all in terms of this element V, which is defined here, and this linear form lambda, which is defined here. These are called the ribbon element and the left integral of the quantum group, respectively. These can be defined in, well, for finite dimensional ones. Right, so again, the main point here is that in the case of SL2, I can give you very, very explicit formulas, each of these elements of the mapping class group act kind of locally on this tensor product. So alpha and beta, so yes, alpha j and beta j, they act only on the jth component, and gamma k acts on the kth and k plus 1 component. Right. So anyway, apart from the details of these formulas, what I can at least tell you is that already from the quantum side of the construction, we can say something interesting about these representations. For instance, you can prove that the action of every den twist along an essential simple closed curve in the surface sigma G1 is always given by infinite order matrix in the projective linear group. And this is something which is a phenomenon which is specific to this non-semi-simple version of TQFTs. So in the semi-simple case, this is never true, right? So this is marks a sharp contrast with respect to the semi-simple case, and this should tell you that well, the motivating questions behind this project are interesting, are more interesting in the non-semi-simple case. Right, very good. So this is more or less all I wanted to tell you about the quantum side of the construction. I decided not to explain the universal construction approach. First of all, because you already saw the universal construction a little bit in this conference, and also because I would like to save some time to tell you something about the homological side. But yeah, so this kind of very explicit definition by formulas is actually just like is obtained by figuring out the details of a more general definition that is that works in a much greater generality than the generality at which these formulas hold. right? Okay, anyway, so now I will move on to the homological side of the construction, and I will also need to fix some notation for this part. And so I recall that conf and sigma g1 is the notation I use for the nth unordered configuration space of the surface sigma g1. So explicitly, this is the set of subsets of sigma g1 of cardinality n, exactly n. So where all these points in this n tuple here are pairwise distinct. And now conf minus, this part of the boundary I was mentioning before, is made up of exactly those configurations of points that have at least one of their components inside this delta minus part of the boundary of the surface. So I draw this in red, and in this picture, delta minus is this kind of left side of the square. And right, so conf minus is the set of those configurations that have one point on this red interval. And now pi sub ng is the fundamental group of this configuration space. So this is, again, this is called the surface braid group for sigma g1. And here, to be more precise than earlier, I specify a base point psi. And since this is supposed to be a base point in the configuration space, so this is given by an n tuple of points, and it's convenient to take this n tuple of points to all lie in the boundary of sigma g1. So in this example, I'm drawing them here on the bottom side of this square, right? So every point in this configuration space is an n tuple of points, and this is my preferred base point. Very good. Now, as I said at the beginning, we will be considering homology with twisted coefficients. And let me recall you very briefly what do I mean by this? This is classical, but whenever we have left z pi module v, and z pi here denotes the group ring for this surface braid group, right? So whenever we have a left module over this group ring, then the homology of this pair with twisted coefficients in this coefficient module is by definition the homology of this complex here. We are taking here on the left chains, so relative chains actually, in the universal cover for this configuration space. And since we're taking relative homology, when you take the universal cover here of the first term, you should also take all the union of all possible lifts of this to the universal cover. So this is pi minus 1 of this comp minus, right? So you take chains in this space, and you tensor over the group ring with this left z pi module v and g, right? And so this is naturally, this is by definition a left z pi module. This is also a z pi module because pi acts by back transformations on the universal cover of the configuration space. This is typically written as a left action, but we can turn it into a right action by requiring that every element of the surface braid group should act by its inverse. Anyway, so this is kind of the definition for homology with twisted coefficients in some module. And like a comment here is that we will use Borel-Moore's version of homology. So I won't go into the details for this definition. This is sometimes also called locally finite homology. But essentially, this is a version of homology that differs from standard one for non-compact spaces. And since these configuration spaces are not compact because we are removing essentially, so we are taking the nth product of sigma G1 with itself. We are acting by permutation with a symmetric group, but we are first removing points which have the same, which have pairwise equal coordinates. So this is a non-compact space, and it will be important, at least for computations, that we use Borel-Moore's version of homology. The construction can be done even without this version of homology, but we want to recover the quantum one, so it will be important that we use this particular version. Right, and now I can tell you maybe a trick that dates back to the work of Bigelow. It has since been kind of used effectively by Jules Martel, my co-author, but also by Blanchet, Palmer, and Shaukat. And this kind of trick allows you to compute these homology spaces of configurations, which have a very simple description, it turns out. So for every left Z-pi module, VNG, so this is kind of independent of what coefficient module you're choosing. The nth homology of this pair, where you're taking n configurations, so n points of configurations here, and you're taking the nth surface braid group, then this homology space is 0 every time m is different from n, and it's equal to this vector space as a linear space exactly when m is equal to n. So this homology is concentrated in degree n. And this vector space is just a direct sum of copies of the coefficient module. And the number of times you need to take this as a direct summand can be computed as this binomial. So this is a formula that can be obtained. So essentially, this is a result that can be generalized to every surface that retracts by deformation onto a graph. And then in that case, you will need to replace this 2G by the number of edges that appear in that graph. And very good. So a basis for this homology spaces, for the nth one, the only non-trivial one, looks like this one, right? So here I draw a picture to represent an element of the base of the basis. So here I'm focusing on the jth one handle, and I'm drawing two curves. One that follows the let's say the meridian and goes back to the delta minus part of the boundary, and the other that goes along the longitude. These curves are dotted and they carry labels. These labels are given by natural numbers, and they are required to sum together to the number n at which you're looking the homology. And okay, so this gives you these many vectors, and then you tensor with a basis for the coefficient module, right? This will give you a basis. And in this picture here, I'm claiming that these dotted intervals, they represent cycles in this relative cycles in this homology space. The way to see this is that you should think that a dotted k-labeled interval should denote the image of a singular open k-simplex. So open simplices, if their open ends behave well, they form cycle in Borel-Moore homology. And the way to understand an interval as a k-simplex is by understanding this as by essentially looking at this specific parameterization of a standard k-dimensional simplex. So a k-dimensional simplex can be identified with a subset of Rk of, right, so k tuples of real numbers between 0 and 1, which are ordered in this way. And so much like when you have an interval, you can understand this as an interval in a surface. You can understand this as the image of a one simplex. Then a dotted interval in this surface is supposed to represent a k simplex in the configuration space, right? So, and you should map all these points in this simplex to the configuration space along, so using this embedding of this interval. Right, so what I told you is almost precise, not really. So actually, these dotted intervals, they represent homology classes in the configuration space, and we should really look at homology classes in the universal cover, right? Because twisted homology requires going to the universal cover and then tensoring by this module of coefficients. So what we actually do in order to, so I mean, every simplex can be lifted to the universal cover, but there's an ambiguity on how to do this. You can choose multiple lifts. And so to precisely fix what we mean by a picture like this, I claim that it's sufficient to choose paths that relate, that join some of the base points. Well, when you consider all handles together, it will be all of the base points. All of the base points to these dotted intervals. And I claim that this choice specifies uniquely how to lift, and so how to interpret this picture as representing actually a simplex in the universal cover and not just in the configuration space. Right, okay. So now I need to tell you how to define the module for local coefficients that we will use in order to recover the quantum representation. And everything I said before kind of works every coefficient module. Now I'm going to fix the choice that kind of enables us to recover the quantum side. And to do this, I specify generators for the surface braid group. So I recall to you that this fundamental group of the configuration space by three kinds of generators. Well, it's mainly two kinds of generators. So we have these sigma I generators. These are like pure braid generators, like standard braid generators, classic braid generators. And then we have surface braid generators, like these alpha J's and beta J's. So the sigma I's are, so you should think that elements in the surface braid group are loops in the configuration space that start from the base point. So start from this n tuple of points on the bottom boundary. They go around, they go around the surface looking at unordered configuration spaces, but essentially these are n tuples of loops. And for the generators, we can choose very simple n tuples of loops. So these sigma I's are defined by keeping all base point fixed, so trivial loops for all base points except for the ith and I plus first, which should do a crossing like in a braid, like in standard braid generators. So these are called sigma I's. And then the alpha J's and beta J's are those generators that keep all base points fixed except for the very first one that moves along the surface following standard generators for the fundamental group of the surface. Okay, and I claim that these provide generators for the surface braid groups. Very good. And now using these generators, I can give you a definition for the local coefficients we need to use to recover this isomorphism. Okay, as it happened before, the explicit definition is maybe not that important. Certain things or certain aspects of it are important, but the fact that there exists a very explicit definition is what allows us to really check the isomorphism. Right, so this Z pi module structure on V and G So VNG, I recall to you, this is just C to the power R to the power G. And this action is defined just by a representation of the surface braid group into the general linear group of this vector space. And it's determined by sending all standard braid generators to a scalar matrix. So just Q to the power 2 minus 2 times the they are sent to matrices which are defined recursively. So for G equals 0 for the sphere, well, you have no surface generators. So this is a trivial case. For G equal 1 for the torus, you just have two of them. You just have alpha 1 and beta 1. And in this case, you should choose, I claim you should choose these two matrices. And the important point about these two R by R matrices, and again, I recall to you that R is the order of the root of unity, is that, so this is the diagonal matrix. On the diagonal, you can see all the powers of Q appear. And this is just a permutation matrix. And the two important points about these matrices is that they Q commute, or rather they Q to the 4 commute. And so the commutators between these two matrices is Q to the power 4. And also they both have order R. Another important point is that their centralizer is just scalar matrices. So something that commutes with both of them needs to be a scalar matrix. And with these two matrices, we can extend this definition to higher genus surfaces. This is done monoidally, essentially. So you should simply, for when J is strictly smaller than G, you should take what you had previously and tensor by the identity on the last component. And when J is exactly equal to G, you should take the identity on the first G minus 1 components and then tensor by A1. And the same for B. Anyway, again, not all the details are important, but we have a very explicit definition. And then very quickly, so I have 5 minutes left. Let me that the U-module structure and the mapping class group, these homology spaces, are really homological in nature, right? So that they can maybe provide good insight on going on for the quantum construction, right? So if we denote by curly H with subscript N and G, just this homology space. So this is one of the pieces of one of the summands of the direct sum that I had before I introduced this curly HG, which was a direct sum of all these spaces for N between 0 and R minus 1. And maybe I didn't mention this, but I should mention, when you change, you're changing the number of configurations, so you're changing the manifold of which you're looking at of which you're taking homology. You're changing the order of homology, so the degree of homology. You're changing the group over which you're taking local coefficients. So again, this is maybe a subtle point, but okay. And then for these spaces, we can define the action of generators of the mapping, of the quantum group E, F, and K really homologically. So for instance, the action of the generator E is implemented by the boundary homomorphism in the long exact sequence of the pair conf n and conf n minus, right? So actually, well, at least. So if you do the boundary homomorphism, you will start from here and land in this space, which is not quite this space, but it's isomorphic to it. You can choose an isomorphism from this to this. And so these are configurations where one point is forced to lie on the interval, and you can choose a way to kind of forget about this point and go and land here. And then the action of F1, so F1 is just a divided, so the first divided power of F. This is just a scalar multiple of the generator F I was using before, which is more natural from the homological point of view. And the action in this case is given by taking, well, any homology class you might have here and adding to it a copy of the complementary part of the boundary with respect to delta minus. So if we call this delta plus, the black part of the boundary, you just take a parallel copy of this, and you need to add a base point and choose a way to join it to this curve. I do this like this. And here I didn't specify any label because the label is 1. Right, so this will implement the action of f. And now with if you just define k to act as a scalar on all these spaces, and this is the coefficient, then the claim is that these two generators, they satisfy the bracket relation I had before, right? So commutator between E and F1 will be K minus K inverse, right? And this is very homological. And now maybe, okay, 2 minutes, I will just end with this point. So just very quickly how you define mapping class group representations, like projective ones. A warning is that you could naively think that it's sufficient to just, so like the mapping class group naturally, you take a homology class and you just twist it using a diffeomorphism. And it turns out that, so it's easy to see that the mapping class group of the surface F kind of injects into the mapping class group of the configuration space. You just, if you have an n tuple of points, you act on each of them with F, right? And this defines the image of F. And this can be lifted to the universal cover because we're looking at surface with boundary. We can just fix a point, a base point in the boundary, and choose like coherently lift for all of these elements. So essentially, this mapping class group can be realized as a subgroup inside the mapping class group of the universal cover of this configuration space. And so we could think that in order to act on a twisted homology class, so this is given by some sigma tilde tensor, some coefficient, it would we could think it's sufficient to act on the left hand side, but this is not true, and this is because twisted homology is not functorial with respect to diffeomorphisms, right? So this chain of equality should tell you that if you well, that this action is well defined only for those mapping classes that kind of induce that fix all elements of the surface braid group. And so the way to fix this is to find a representation for the mapping class group. There's a mistake here, actually. This is not a representation. I should write a projective representation, but anyway. So there is a map from the mapping class group to here, and this is where like the projectivity arises. And if you untwist the coefficient using this very explicit map, then this will allow you to define a projective representation of the mapping class group. And now the main statement I recall is that what I defined just now, so the U module structure and the mapping class group representation, they coincide with what you had on the quantum side. So this provides a homological model for these representations. So my time is up. I will stop here. Thank you very much.
Questions for Marco?
Thanks for the talk. So I'm wondering, you said something very briefly about faithfulness. What is the status on that? And also, I think I got a bit confused, like how big does R need to be in relation to any of the other quantities?
Okay, so the status of faithfulness is that for the moment, we know 3 of the mapping class groups to be linear. Well, I mean, three of the general to be, I mean, we know that the sphere has well, a trivial mapping class group, so this is linear. The torus has a mapping class group which is explicitly linear because it's isomorphic to SL2Z, and it was proved by Bigelow and Budney that the genus 2 surface has also a linear mapping class group. So there exists a faithful representation of very big dimension, and this is based on the proof. On Bigelow's proof of faithfulness for braid group representations. So for the 4 punctured disk, so 4 punctured sphere, sorry, and they use this to kind of deduce using the hyperelliptic involution of the genus 2 surface, faithfulness also for that mapping class group. For all the other surfaces, this is just open, this is unknown, we don't know. So this is maybe concerning your first question. And for the second one, right, so R is just an arbitrary odd integer, and you can take your favorite one. And so I mean, in the semi-simple theory, you have plenty of results that are very interesting, very deep, and that concern the limits where R go to the infinity. So maybe this is also something that will pop up in the non-semi-simple case, but you in principle R here can be any odd integer greater than 3, and all the other numbers. So I know, I realize there is a lot of notations, and I'm sorry about this. So Jules has a nice way of presenting this, keeping notations fixed on one part of the slide. I didn't have time to prepare this, but yeah. So some of these quantities, some of these numbers I'm using here, they should be smaller than R. For instance, n here, I always will take it to be between 0 and R, but G is just an independent number. It's just the genus of the surface. And yeah, I don't know if this answers your question.
It does, thank you.
Other questions? Well, if not, let's thank Marco again.
Thank you, everybody, for coming.
Don't forget to like and subscribe. Stop recording.